Hello, everybody. Hope you're having a good day. Uh, the lecture today is going to be a little bit of basic physics. We're about to pivot in the course to digging into some more details about how systems work, not just stars, but eventually planets and lots of things in the rest of the universe. And to do that, we really need to understand how things like motion and gravity work, because we're going to see them in action for the rest of the semester. So let's take a half a step back, talk about these basic principles of physics so that they make some sense when we see them in practice. All right. Um, it's an it's a deceptively simple question to ask, why do things move the way that we see them moving in the universe? And it actually took thousands of years of people uh, arguing and trying to figure out exactly why things move in the way that we see them moving in the world. Uh, and one of the first people to really start getting a good handle on it was Galileo. And Galileo realized that things don't just get up and start moving on their own, which is, again, trivially obvious, but also that when things start moving, they have a tendency to want to keep on moving. That objects that are already in motion want to just keep on doing that motion, moving in a straight line with a constant speed. And so Galileo called this tendency inertia. Right? The word inertia literally just comes from the Latin word for laziness, right? Things in nature are lazy. They want to just keep on doing what they're already doing. If an object isn't moving, it's going to keep on not moving. If an object is moving, it wants to just maintain that motion. And so Galileo called this principle the law of inertia. That that things just want that objects want to maintain whatever their motion already is, and that in order for something to change its motion, that requires some kind of a force. Something has to happen to the Something external has to happen to an object to get it to change its motion, because in the absence of any external forces, things are just going to keep on doing what they're already doing. All right. Um, when I say force, that the idea of force in physics can seem a little abstract because there are lots of different kinds of forces, right? You can have pushing, the force of something pushing or pulling, or springs, or the force of gravity, or the force of magnetic forces, electric forces, right? There's lots of different kinds of forces in nature. But the one thing they all have in common is that a force is something that causes an object to change its motion. Right? If any object is changing its motion, either speeding up or slowing down or changing direction, if an object's motion is changing, by definition, that is happening because a force is acting on it. Then the question is, well, what is that force? But that's the deeper, more interesting question, right? If an object has no forces acting on it, it'll just coast. It'll coast, moving in a straight line at a constant speed under its own inertia. Right? And this is what you tend to find in space, right? In space, there's not a lot of friction to slow things down. Friction is another force, right? Friction is a force because friction always wants to slow things down. But in space, you don't tend to have a lot of friction, and so it's a lot easier once you're in a frictionless environment like just floating out in space, that if something starts moving, it's just going to keep on moving. It's going to keep on coasting under its own inertia. So Galileo puts forward these ideas, and then decades later, Isaac Newton comes along and starts doing his own investigations into things like motion. And in fact, I mean, Newton did a lot of investigations into everything. Newton was the one who discovered that you could take sunlight, shine it through a prism, and break it up into the rainbow. Newton was the one that discovered the spectrum of the sun, and that the sunlight is made of all the colors of the rainbow. Newton was one of the co-inventors of calculus. So Newton did a lot of things, and Newton has a big place in a physics textbook, mostly because he did lots of experiments in lots of different fields, optics and spectra, but also the invention of a whole new branch of math in calculus, and also investigations into why things move and how gravity works. So he's kind of one of the big names for the lecture today. A little bit of vocabulary. When we talk about speed, what is speed, right? Speed is how fast you're going, right? Speed is the distance that you can travel in a unit of time, right? Speed is how far you travel in 1 unit of time. So if you get in your car and you're traveling at the speed of 60 miles per hour, that means you can travel a distance of 60 miles in 1 hour of time. In everyday English, speed and velocity mean basically the same thing, right? In normal English, speed means the same as velocity. But in physics, velocity means something more specific. In physics, the term velocity is both the speed you're traveling, but also the direction you're traveling. And so you might be in your car driving at 60 miles per hour. That's your speed. But your velocity could be 60 miles per hour south. Why does it matter? Well, because in the context of inertia, you could be driving in your car 60 miles per hour south, and if you take your foot off the gas, your car is just going to keep on coasting 60 miles per hour south. If your car is just coasting because you took your foot off the gas, it's not going to all of a sudden start moving 60 miles per hour north, right? So Newton took these ideas from Galileo. Newton started from the point of view of Galileo's idea of inertia, and then he tried to build on it to say, okay, what else can we figure out about how motion works? So Newton ends up coining 3 laws of motion, the first of which is basically a restating of Galileo's law of inertia, that an object at rest will stay at rest, or an object in motion will stay in that motion unless acted upon by some outside force. Right? So in this example here, right, if you've got 3 balls on a table, ball A is not moving, it's just going to keep on not moving. If ball B is rolling across the table with some constant speed, then it's just going to keep on rolling with that constant speed in a straight line at a constant speed, which is to say, with a constant velocity, right? Ball B is rolling across the table with a constant velocity. Velocity is speed plus direction. So if it's rolling with a constant speed in a straight line, then ball B is rolling with a constant velocity. Just like your car would be, right? If your car is driving 60 miles per hour south and you take your foot off the gas, it's just going to keep on coasting under its own inertia with a constant velocity. If ball C is rolling across the table, it's traveling with a steady velocity until it gets to right here, and then let's say you poke it, right? You poke the ball, you exert a force on it, and that force changes the velocity of the ball so that now it's moving off in this direction. So Newton's first law of motion basically says objects are just going to keep on moving with their constant velocity unless some force acts on that object to change the velocity. Right? So what is a force then? A force means something specific, again, in this physics vocabulary. A force is any phenomenon that changes the velocity of an object. Right? If an object's velocity is changing, that must be because there's some force causing the change in velocity. If an object's velocity is changing, then that velocity must be changing with a certain acceleration. So what is acceleration? One more piece of vocabulary here. Acceleration is the rate of change of velocity. So the acceleration is how fast the velocity is changing. Acceleration is how fast is an object speeding up, how fast is it slowing down, or how fast is it changing direction. Right? So if there's some force acting on an object, then the velocity is changing. If the velocity is changing, then the velocity must be changing with some acceleration. The velocity is changing at some rate. All right. So what Newton's second law says is that the force that's acting on an object is proportional to its acceleration, right? If you take a softball and you throw it, well, if you throw it harder, if you exert a greater force on it, it'll speed up faster. If you throw it with a weaker force, it'll speed up slower. So the acceleration that the object speeds up or slows down by is proportional to the force. Stronger force, faster acceleration. But the acceleration that the object experiences is inversely proportional to the mass. If the object being pushed is more massive, then it's going to speed up slower. Right? If I take a softball and I throw it, it speeds up pretty fast. If I take a bowling ball and I throw it with the same force, it's not going to speed up as much. Why doesn't the bowling ball speed up as much? Because it has more mass. And then we've said this before in class, but a reminder, right? What do we mean when we say mass? Mass is how much matter an object is made of. Right? If I throw a softball and a bowling ball, that bowling ball is going to accelerate a lot slower, even though the force I'm pushing on it is going to be the same, but I got to move more mass. And if I've got to move more mass, that mass is going to move slower. It's going to speed up, accelerate slower. Okay, so Newton's first law says, just to reiterate myself here, Newton's first law says changing velocity requires acceleration. Changing velocity requires a force. Newton's second law says the acceleration that you get is proportional to the force, but inversely proportional to the mass. Newton's third law says that when you have a force, you always have a reaction force also. Right? Forces always come in pairs. That when one object is exerting a force on another object, that second object exerts an equal force in the opposite direction back on the first object. This is usually Newton's third law is phrased as, for every action there's an equal but opposite reaction. Right? When one object pushes on a second object, let's say you are pushing on a wall, right? Your body is exerting a force pushing on the wall. Well, if you're pushing on the wall, then the wall is going to push back on you, and the reaction force is always equal in strength but opposite in direction. If you push on the wall forward, the wall pushes on your body backward, and your body is going to accelerate backward, right? When you push on a wall, your body accelerates backwards. Why is your body being pushed backwards? Because the wall is exerting an equal but opposite force back on your body. So Newton basically boiled down everything that he could think, everything that anybody was thinking about motion, forces, velocities, accelerations, and Newton boiled it all down to these three principles. Right? The first law is that changing velocity requires a force. Newton's second law says that the acceleration that you get is proportional to the force, but inversely proportional to the mass. And that Newton's third law says when you have a force, you also always have a reaction force in the opposite direction with equal strength. Okay. Newton's three laws of motion work for anything in the universe. Everything in the universe moves according to Newton's three laws. Because Newton's laws are very abstract. Newton's laws are very general. They're just talking about any object's velocity, any force. And so if there's a force acting on an object, things are going to move according to Newton's third laws, regardless of what the force is. Pushing, pulling, springs, magnetic fields, electric fields, gravity. So then Newton said, okay, these seem to work fine, but can I use my understanding of how all forces work to understand the force that's keeping, let's say, the moon in orbit around the Earth? Right? What can we say about this gravitational force that is pulling the moon, that is keeping the moon around the Earth? There must be, right? If the moon is orbiting around the Earth, then the moon is constantly changing direction. One day the moon is moving this way. A few days later, now it's here and moving this way. A few days later, it's here and moving this way. A few days later, it's here and moving this way. As the moon goes around the Earth, the direction of its travel is constantly changing. And if the direction is changing, the velocity is changing. And if the velocity is changing, there must be a force acting on the moon. Well, gosh, where's the force coming from acting on the moon? It must be the Earth. And this is where Newton came up with his universal theory of gravitation. Basically, Newton was the one who put all these ideas about what is a force, what is velocity, put it all together to say, come up with one theory for how all gravity in the universe works. There were a lot of ideas before Newton about how gravity works, but a lot of those ideas played around with the notion that gravity works differently on Earth than it does up there in space, or that the gravity works differently on Earth versus the sun and other planets and stars. There was a lot of the rules that people were making up were very inconsistent. To say that, oh no, the laws of nature work differently on Earth than they do over on Mars or Venus or Jupiter. Newton says no. No. Newton says gravity works the same everywhere. And that it's the exact same gravitational force holding you on the Earth's surface. It's the same gravitational force holding the moon around the Earth and the Earth around the sun and all the planets around the sun. Gravity works the same everywhere. How does gravity work? Well, Newton said, gravity is a force between two objects. So let's call them, in my little cartoon here, we'll call these objects, object 1 has a mass m1, object 2 has a mass m2, and those objects are a distance r apart. Newton says the gravitational force, so F1 will be the force on object 1 from object 2, F2 will be the force on object 2 from object 1. Object 1 and object 2 are pulling each other together. Why? Because for every force, there's an equal but opposite force. F1 and F2 are equal in strength, but they're pulling in opposite directions. This is why gravity is always attractive, right? Gravity always attracts objects together, because if M1 is being pulled toward M2, then M2 has to be pulled toward M1. If one force is pulling to the left, the other force has to pull to the right, and they get pulled together. This is why gravity always pulls things together. And that the strength of that gravitational force, F1 and F2, is equal to the mass of the first object times the mass of the second object divided by the distance between them squared, so that the gravitational force is stronger if mass 1 is a larger mass or if mass 2 is a larger mass. So if either of those masses are higher mass, you get a stronger gravitational force. But if those objects are farther apart, if r is greater, then the gravitational force gets weaker, right? If you're dividing by a larger distance, then the force gets weaker. So the gravitational force is strong when the two objects have really high masses and they're close together, or both. The mass of the first object, the mass of the second object, the distance here, that all ends up getting multiplied by this big G. Big G is what's called the universal gravitation constant. This is just another constant of nature. Big G here is the number that is baked into our universe that determines how strong the gravitational force is in this universe. So it's just a number. And that number is pretty small, right? 6 times 10 to the negative 11 is a small number, because when you've got objects that are low mass, right? Low mass objects like, people and cars, right? Low mass objects don't actually exert that much gravitational force on each other, right? You're taking objects that have moderate masses and then you multiply by this tiny, tiny number g, well, then the gravitational force is really weak. It's not zero, it's just really small. Gravity only becomes the dominant force in the universe when you're dealing with things that have really high masses. M1 or M2, if M1 or M2 is the mass of a planet or a star, then that's enough mass to make that gravitational force really strong and keep you and I stuck here on the Earth's surface. Or it keeps the Earth stuck orbiting around the sun. So this is the universal theory of gravitation. You can calculate the gravitational force between any two objects, right? M1 and M2 could be the masses of anything. People, cars, planets, moons, stars, right? Any object that has mass. In fact, let me rephrase that. Every object that has mass exerts a gravitational force on every other object in the universe. Gravity is a force between every pair of objects everywhere. But that gravitational force is proportional to the masses, but inversely proportional to the distance. So, yes, your body is exerting a gravitational force on the moon, the sun, Alpha Centauri, the Andromeda Galaxy. Your body is pulling on every other object in the universe. But pretty much everything else in the universe is way too far away. The distance is so great that gravitational force becomes negligibly small. Not zero, but negligibly small. The one object whose gravitational force your body is not negligible on is the Earth. Because the Earth is, pretty high mass, but also we're really close to it, right? We're standing right on top of it. So we're close enough to the Earth that the gravitational force of the Earth pulling on your body, and vice versa, is strong enough to keep us stuck here. So Newton says, okay, wait. Is there a contradiction here, right? Let's say that these two objects are the Earth and the moon, right? The Earth is pulling on the moon is pulling on the Earth and the moon are pulling each other together. They're attracting each other. So they should be pulling together. The moon should be getting pulled down to the Earth, but the moon isn't getting pulled down to the Earth. The moon is going around the Earth, right? Why does the moon go around the Earth when gravity should be pulling the moon to crash back down to the Earth? How do orbits happen? If gravity works like this, then how do we have orbits? Why isn't the moon crashing into the Earth or the Earth crashing into the sun? So Newton says, okay, I'm going to construct a thought experiment. Right? What is a thought experiment? A thought experiment is a what if. Right? What if I do this? Then what would happen? That's what a thought experiment is. All right? So Newton said, okay, what if I dragged a cannon to the top of the tallest mountain in the world? And I'm going to take this cannon and I'm going to go fire a cannonball horizontally. He fires that cannonball. The cannonball's inertia is going to want to carry the cannonball straight to the left, but gravity is going to accelerate it down to the ground. So what happens? Well, the cannonball moves to the left and falls down to the ground. Right? The combination of inertia and force means that inertia makes the cannonball go left, gravity makes the cannonball go down, so it goes down and to the left. If I fire this cannonball faster, though, then the cannonball will have more inertia. So that cannonball's inertia, that cannonball's velocity, will carry it farther before it eventually hits the ground. If I fire this cannonball even faster, then pretty soon the curvature of the Earth is going to become significant here, right? If I fire this cannonball fast enough, it'll travel so far before the Earth's gravity pulls it down to the ground that that cannonball could land behind the horizon. If I fire this cannonball even faster, that cannonball could fly halfway around the Earth and land clear on the other side of the Earth. Right? Why? Because look at what's happening. Right? Gravity is always a force that pulls things toward each other's center. So when the cannonball is first fired, it wants to go to the left, but the Earth's gravity wants it to move toward the center of the Earth. So what does it do? It moves left and toward the center of the Earth, so it moves to right here. But when the cannonball gets right here, now its inertia wants it to go this way. But the Earth's gravity wants to pull it down to the center of the Earth, so it moves in both directions. Right? This cannonball is constantly trying to move forward. It's constantly trying to fly forward under its own inertia, but the Earth's gravity is pulling it, is accelerating it down to the center of the Earth. And so this cannonball is constantly moving forward and down, forward and down, forward and down, forward and down, until eventually its path intersects with the Earth's surface and it crashes into the Earth. If I fire this cannonball even faster, then this cannonball could conceivably fall all the way around the Earth and come back to where it started. What's happening? What's happening is this cannonball's inertia wants it to move forward, but the Earth's gravity is trying to pull it down to the center. And so this cannonball's trajectory is being curved. But if we fire this cannonball fast enough, then this cannonball's path will curve exactly at the same rate as the curvature of the Earth. And so as the cannonball falls toward the ground is curving away from the cannonball. The cannonball doesn't actually get any closer to the ground, and so it can fall all the way around the Earth and hit Newton in the back of the head. This cannonball is now in orbit. This is what an orbit is. Right? Objects orbit the Earth, the moon, or satellites, or rockets, or the International Space Station. Objects orbit the Earth because, yes, the Earth's gravity is trying to pull them down to the Earth, but those objects are moving forward fast enough. Those objects have enough inertia, they have enough velocity that they're moving so fast. The cannonball in this case, it's moving so fast, it's flying so fast that it actually misses the ground entirely, and it falls all the way around the Earth. An object in orbit is not flying. There's nothing propelling it, right? After you fire the cannonball, after you fire that cannon, the cannonball is just flying forward. It's coasting under its own inertia. An object in orbit is just coasting forward while gravity tries to constantly pull it down. An object in orbit is in free fall. It is falling toward the ground. It's just moving so fast that it misses the ground. And it keeps on falling forever. Right? This is how Newton explained objects orbiting, whether it's the moon orbiting the Earth or the Earth orbiting the sun. Gravity is pulling the moon and the Earth together, but the moon is moving forward fast enough that it's never going to hit the ground. It's just going to keep on falling around the Earth continuously forever. If something could somehow slow the moon down until the moon moves too slowly, then the moon would crash into the ground. But at this point, the moon is so big and it's moving so fast, realistically, nothing's going to slow the moon down. Right? Now, realistically, how do we do this? Right? How do we get objects into orbit? And the answer is, well, you can't just, this is why this is a thought experiment and not an actual experiment, because Newton's little thought experiment didn't take into consideration atmospheric drag. It didn't take into consideration atmospheric friction. Right? If the Earth had no air and you fired this cannonball fast enough, sure, this cannonball would just whiz above the Earth's surface, falling forever. Realistically, though, the atmosphere slows things down, right? Atmospheric friction would slow that cannonball down until it came crashing into the Earth's surface. So if you want to put a satellite in orbit of the Earth, you got to get it up above the atmosphere. And the Earth's atmosphere tops out at about 200 kilometers. So in order to put a satellite in orbit, you got to get it 200 kilometers above the surface so that it's above the atmosphere. And then you got to get it moving forward fast enough that it doesn't come falling back down to the ground. The minimum speed to stay in low Earth orbit is about 17,000 miles an hour. That's how fast the space station, the Hubble Space Telescope, telecommunications satellites, those objects need to get 200 kilometers up. And then they need to get going forward. They need to get flying forward 17,000 miles an hour so that they can just fall around the Earth forever and never intersect with the ground. This is why these rockets are so big. Right? When you launch a satellite, the satellite is very small, but you have to take this small satellite and put it on top of these giant rockets. The problem with putting something into orbit is not going up, right? Because all you need to do is get above the atmosphere. All you need to do is go 200 kilometers. What is that? About 120 miles, right? Getting a satellite up 120 miles is a piece of cake, well, relatively speaking. The problem is not getting the satellite up. The problem is getting the satellite up and then getting it accelerated to the point that it's coasting at 17,000 miles an hour. If you can do both of those things, if you can get it up high enough and you can get it moving forward fast enough, it'll stay in orbit, falling around the Earth forever. But that takes a lot of rocket fuel. That's why the rockets that you see launching satellites are so big. And that's just to get into Earth orbit. If you want to escape Earth's gravity altogether, leave the Earth's gravitational pull and go travel to other planets, then you need to get going even faster. You need to get going fast enough that you can move away from the Earth before Earth's gravity has the chance to slow you down and bring you back in. The minimum speed to escape Earth orbit is about 24,000 miles an hour. So that's why when you see the rockets that launch probes to go to Mars or Jupiter or Pluto or something, those require the biggest rockets that people make, because you need to get going not just fast enough to get up and stay up, but fast enough to get away from the Earth before Earth's gravity has a chance to slow you down and bring you back in. This is how we get out into the solar system. right? We can't go and explore the solar system. We can't land people on the moon or land robots on Mars or put probes into orbit around Jupiter or Saturn. We can't get out and explore the solar system if you can't go fast enough. And how fast do you need to go? That requires understanding how gravity works. So it's a big abstract idea, the idea that there's one theory for gravity that explains everything in the universe. And yet, on the other hand, this is quite comforting. This is quite nice that you only need one theory, that there is one theory of gravity that explains gravity everywhere. And if we've got a good handle on this one idea, then we can exploit it and utilize it to get off of Earth and go and see what the rest of the solar system is like. And then, eventually, maybe one day, get out of the solar system and see what the rest of the galaxy is like. Can't do that yet, but maybe one day. So, all right. We're going to explore orbits in some more detail in the next lecture. And so hopefully this is making some sense. And go ahead, and if it is, then go ahead and continue on into the next lecture. All right. Have a good one, everybody.